We want to discuss the concept of probabilities by focusing on probability distribution. I think iko na maana hizo. Tufunge kwanza. Niambie wote tatu. Niambie wote tatu. So we want to look at the concept of probability distribution. Have the discussion of the matrices. In our last discussion, we will look at the matrix. Probability matrices. We were able to obtain the equilibrium point, equilibrium market share. We did focus also on the current market shares of a product or a service. Today, we want to look at probability distribution. But before we look at probability distribution, you need to remind yourself about the concept of probability from the beginning. You need to define what a probability is. What are the basic concepts of foundational probability? Look at the types of probability. Look at the laws of probability. Be able to look at the axioms of probability or the principles of probability. Then thereafter, we're supposed to look at the applications of basic probability. Once you are able to define a probability, you will be able to move on and define a probability distribution. And we are saying that probability, as you may have defined before, is a numerical value that's used to measure uncertainty. A numerical value that is used to measure uncertainty. That is probability. That when you want to determine the occurrence of an event, you can never be 100% sure if the event is going to occur or not. Then we look at the concept of uncertainty. The probability of an event occurring may be between 0 and 1. It is never 1, it is not 0. Some books have defined probability as a quantification of chances or likelihood that an event may occur or not occur based on the available evidence. So then we are talking of the quantification of chances. Now, chances are likelihoods. And if the quantification of chances or likelihood that an event may or may not occur, but based on the available evidence. So the evidence must be available for you to say, yes, the event has occurred, or the event has not occurred. That's how we can also divide probability. And there are two types of probability. That's the experimental probability, and then we also have the theoretical probability. Experimental being objective probability or empirical probability. Theoretical being classical probability or subjective probability. So those are the things we may have looked at before. So once you have been able to go through all these application probability, then look at what is a random variable. Define a random variable. You may have defined before a random variable. And look at a continuous random variable. Then look at discrete random variable. Basically, that's what you are supposed to have discussed in your earlier school days. a continuous random variable, a discrete random variable. Then from this is when you're going to focus on the probability distribution, common probability distribution. And the probability distribution is just a function. Distribution basically is a function that maps a random variable to a possible value. So a function that maps a random variable to a possible value is what we're defining as a probability distribution. It is assigning a random variable to a possible value. So given as probability of x equals to x, this capital X is a random variable. This small x is a possible value. Possible value. So this function that assigns a random variable to a possible value is what we are saying the probability distribution. Some books will say it's an X mapping to X. That is a function that maps a capital X to a small x, a random variable to a possible value. So let's look at commonly used probability distributions. Simple, commonly used probability distributions. We'll look at a discrete probability distribution and a continuous probability distribution. Now, by looking at them, I want to look at first the properties of those probability distributions. But before we look at the properties, at one time we have looked at the measures of central tendency, that's the mean, mode, median. At this level, someone will ask us, why then do we, this particular level, why do we look at the measures of central tendency? Why do we look at the mean? And why do we look at the median? Why do we look at the mode? Of what value, of what significance are these parameters to us? Now, the purpose of looking at the mean, mode, median is to determine the normality of any given distribution. Sometimes we are going to make an inference. We are saying that when you're making an inference, the quality of the inference you're going to make, the accuracy of the inference will be dependent on so many factors. One of the factors will be the sample data. How accurate was your sample data? So then how do you determine that my sample data is accurate? So by the end of the day, when I've done the analysis, I'm going to come with an accurate or correct inference or correct judgment. So we look at the mean, mode, median to determine if the distribution, if the sample obtained from the field is normal or not. So we did say that if the mean and the median and the mode, just because the mode exists, it may not exist. If the mode exists, then the distribution we have is normal. So any inference we're going to make will be an correct or an accurate inference. You see, we are supposed to make an inference at the end of the day. We are saying you identify the problem in the society, proceed to the field, collect the data, analyze the data, make an interpretation, and finally make an inference. The inference we're going to make will depend on the interpretation that will have depended on the analysis, the outcome of the analysis. So how accurate is the analysis will be defined by the type of data that one may have collected from the field. So once you have been able to send such a field, they will be able to bring for you sample data. But then based on the sample data given to you, you need to determine of this sample data sent to you, which is the most accurate, which is the most consistent sample data. That's why I'm saying you need to look at these three variables, the mean, the mode, and the median. But in most cases, sometimes the mode may not exist. So look at only the mean and the median. But if the mean and the median exist, and the mean and the median are approximately equal, then the distribution we have is going to be normal. But if they are not equal, sometimes you may work out the mean and the median, if the mode exists and the mode, and these three variables are not equal, then the distribution will be said to be skewed. So any inference you're going to make about that particular sample, that particular distribution, is going to be a wrong inference. You're going to make a wrong judgment. And by the end of the day, somebody will say, this person has been making a very good inference, has been making a very good judgment. What has happened to him or her today? It's because of the quality of the data you are basing on to make an inference. So if your mean and the median are not equal, then the distribution you have been given is not accurate, it's not reliable in making an inference. So what we are saying, why we learn these variables is to determine the distribution we have. Is it correct? Is it accurate? Is it reliable or not? So approximate, of course, you cannot find the mean and the median being the same. They may be approximately equal. It's from this that will come the properties of some basic probability distribution. So I want to start looking at a normal probability distribution. Yeah? A normal probability distribution. Now, a normal distribution one is that it must have its mean, median, and mode the same. That is the basic property. That unless the three are equal, the distribution is not normal. But if they are going to be equal or approximately equal, they will say the distribution is normal. Then you can proceed and use it to analyze and make an inference. So if the three are equal, then we say this is continuous and symmetrical. It cannot be continuous and symmetrical if they are equal. Otherwise, it will be skewed. Now, a skewed distribution, we say it's a symmetrical distribution. Just a symmetrical distribution. Even the data they're going to make will be asymmetrical. But when the data is normal, we're going to make symmetrical inference of symmetrical judgment. So when the two are equal, we say continuous, symmetrical. Then a normal distribution is always unimodal. It has only one mode. So a unimodal distribution has only one mode. And a normal distribution does not have one mode. We are going to say that in a standard normal exam, if an exam is set, students sit for the exam, then you find it has a bimodal distribution or a multimodal distribution. It has more than one mode. That exam is not standard. So that's why we say a normal distribution must be unimodal, must not have one mode. Then we also say the tails of the curve, I want to plot the curve. The tails of the curve are asymptotic to the baseline of the curve, are asymptotic to the baseline. They will always approach the baseline, but they will never touch the baseline, asymptotic to the baseline. This means they will converge in some value, but they will never be able to reach the baseline. So if this was our normal distribution, then you realize that these tails on either side, the left and the right, are approaching the baseline, but they're not touching the baseline. What we are saying, under normal circumstances, you can never have 100% confidence level. We talk of 99% confidence level, 95% confidence level. We don't talk of 100% confidence level. We cannot find a situation where everything is perfect and the mean and the median are perfectly equal. So the tails will approach the baseline, but I've always said they will never touch the baseline. There is no situation, there's no perfect society in this world. So this point is where we have the mean, the median, and the mode. That point of the peak, the highest point. Now the tails on the right and the left approach the baseline, but they're not touching the baseline. There is no perfect situation. So we are always saying that I've always told people sometimes in the spiritual world, when you fast and pray 24 hours in a day, 7 days in a week, 52 weeks in a year, you will not become Jesus Christ. But you only become perfect as you approach Jesus Christ. So you are not talking about a human being being 100% perfect. You say the tails of the curve approach the baseline, and they never touch the baseline. Now, when you look at a normal distribution, the formula of a normal distribution, we say is f of x, which is probability of x equals to x, is equal to 1 over the root of 2 pi sigma e raised negative 1 over 2 x minus mu over sigma squared. That's a normal distribution formula. But you see, I'm not saying we're going to use this formula. What I have is that 2 is a constant, 1 is a constant, pi is a constant. This is 22 over 7, 3.142. Then e is a constant, that's exponential sign, 2.718. So what then we have is only sigma, mu, and x. But you are looking for x. That means you only have sigma and mu. And at the beginning, I said the mean of a population is given as mu, and the standard deviation of a population is given as sigma. So then that means a normal distribution has only 2 parameters. That's now point number 5. There are normal distribution has 2 parameters. And those parameters must be defined. Otherwise, you will not be able to find the value of x. So normal distribution has 2 parameters, i.e., the mean mu, and then the standard deviation sigma. Those are 2 parameters that are there in a normal distribution. We'll just say from the formula, 1 is a constant, 2 is a constant, pi is a constant, a is a constant, half is a constant, 2 is a constant. So we are looking for x. We are looking at the expected lifespan. That means you're looking for the value of x. Then the other values, the mu and the sigma must be given, must be defined. That's what you're saying. A normal distribution must have two parameters. If they do not exist, then you cannot be able to use a normal distribution to find the probability of an event occurring or not occurring. Then number 6 is that the area between negative, this negative infinity, that's positive infinity. That means the area under the curve. Area under the curve. I.e., between negative infinity and positive infinity is 1. Sum of all probabilities is equal to 1, never more than 1. So between negative infinity and positive infinity, the area under the curve is equal to 1. And then when we say it's symmetrical, if you know the left-hand side and you know the right-hand side, it's obvious. If x is known, then y is known. Then you also say, well, look at the shape of the curve. Of course, someone will say it has a bell or dome shape. Bell or dome shape. Then the quartile or the percentile. This is quartile, this is Q1, and this is Q3. The distance from the first quartile, the central point, I mentioned central tendency, from the central point to the third quartile is the same. So this distance is equal. That's why we say either the quartile or the percentile are a distance from a measure of central tendency. That is from the mean. We are dealing with the mean. The distance from the first quartile to the mean, and from the mean to the third quartile is always equal. So that is a normal distribution. So when you find the integral value of a normal distribution function with respect to x, you'll finally get 1. So if I was to integrate this function, for example, integration of f of x dx from negative infinity to positive infinity, where f of x is integration of 1 over 2 root 5 sigma e raised negative 1 over 2 x minus mu over sigma squared dx from negative infinity to positive infinity. This is equal to 1. That is when you integrate that function. But sometimes we say it is cumbersome, it is tiresome, it is tedious to find the integral value of a probability distribution function. So this has been normalized. When a normal distribution function is normalized, then we get the pi code. So what we are going to focus on, we are looking for x, then mu and sigma must be given. Where do we have x? That is the point. So therefore, the set score, that is the value then, is equal to x minus mu over sigma. This value in the brackets. When this is a normalized, this is a normalized normal distribution function. So the rest have been done away with. So we have it x minus mu over sigma, this is a set score. Now, when you simplify this, then you get pi over x. So that then will give us the probability of any given value, as long as the interval has been given. So that is a normal distribution, which is a continuous distribution. But I'm saying it will only be normal if the mean and the standard deviation have been given. If mu and sigma have been given. What if they're not given? Then we have, look at the three of them straight away. Then we have a binomial distribution. Yeah? Sometimes it may be normal, but it do not have the mean and the standard deviation. It is not possible for one to find the mean of a normal distribution. Not possible for one to find the standard deviation of a normal distribution. That's why we now want to approximate. But how do we approximate? We then going to approximate by using a binomial distribution. So a binomial distribution, we are given as f of x is equal to n over x, dx, how to define the variable first, q n minus x, where n is a sample size. Now, n is a number of crayons. Number of crayons. The number of attempts. Then how many times are you going to attempt? How many items have been delivered over the departmental store? How many items do you have? So that is the value of n, is a sample size. The number of trials, the number of attempts. Now, P is the probability of success. Probability of success. And if P is probability of success, then automatically implies that Q is the probability of failure. There are only two possible outcomes. When you test an individual for a disease, is either the individual is infected or not infected. When someone sits for an exam, an experiment, there are only two possibilities, either passing or failing. You cannot have halfway pass, halfway fail. You either pass or you fail. So if P is known, then Q is known. What do we say? P plus Q must give you 1. That is that if P is known, then Q is equal to 1 minus P. If I remove success from the total, then the remaining is failure. If someone supplied to you 10 chairs, and you say, out of the 10 chairs supplied to me, 2 of the chairs are faulty, that automatically implies that 8 are good. So if you know Q, then you know P. If you know P, then you know Q. Because an item is either infected or not infected. An item is either good or not good. There's no way of saying halfway good, halfway bad. So this is a formula for binomial distribution. Now, binomial distribution is a discrete distribution. I know you know what discrete means, discrete distribution. We say a normal distribution is a continuous distribution. When we talk of discrete data is data that's countable. This is data is countable. But now continuous data, it is data that is measurable. This is data that's measurable. So there's a difference. You can never count the height. You can never count the distance. But then you cannot measure the number of persons. You only count if it's discrete. You only measure if it's continuous. So a normal distribution is continuous. For example, I give an example, the expected lifespan of an African, the expected lifespan of a tube, the expected lifespan of a vehicle, that's a continuous. But when you talk of the number of persons, number of items, then that is discrete. So a binomial distribution is a discrete distribution. Now, this distribution is used as an approximation. Used as an approximation to a normal distribution. Approximation to a normal distribution. I said, for a normal distribution, you must have the mean, the standard deviation. But in a situation where there is no mean and there is no standard deviation, then you will approximate the normal by using binomial. It's so simple to find the mean of a binomial, so simple for you to find the standard deviation of a binomial distribution. Therefore, we cannot be able to approximate now for normal. We use binomial to approximate for normal when the mean, mu, and all standard deviation, right? Standard deviation sigma are not defined. Not defined means not given. So if one of them is not given, or if both of them are not given, then you cannot use a normal distribution. So you approximate then that normal by using a binomial distribution. So that is the second property of a binomial distribution. Then we can be able to proceed and say the mean of a binomial distribution is more than the variance. The mean, we'll be able to find the mean and variance later on. The mean is more than the variance. Now, the variance of a binomial distribution is equal to the mode. So the variance is equal to mode. Now we have just said that the mean is more than the variance. And the variance is equal to mode. And that automatically implies that the mean is more than the mode. And if the mean is more than the mode, then this distribution is positively skewed. This is positively skewed. Then we also define it has a finite number of trials. That means N is defined. N is known. That means it's a finite number of trials. Now, in a trial, there are possibilities. There's a P or a Q. There are possible outcomes. So we say the trials or outcomes are independent from each other. They are independent from each other. So the occurrence of one of the events cannot influence the outcome of the other event. And then the two events cannot occur at the same time. Now, this binomial distribution becomes symmetrical if the probability of success and failure is a set. It is symmetrical if P is equal to Q. If the probability of success is 50% or 0.5, that means Q is 0.5. So if the two are equal, then the binomial distribution is said to be symmetrical. Then from binomial, I want to look at the properties first. We then have a Poisson distribution. Poisson distribution. So those are the basic three probability distribution functions we need to discuss. So Poisson distribution, this is also a discrete distribution, but defined as f of x, or a probability of x equals to x. This is a probability distribution function. A random variable, a possible value, is equal to e raised to negative lambda. If I use the lambda form, lambda raised to x divided by x factorial. We'll define that, where x is either 0, 1, 2, up to n, and n representing to infinity. So E is an exponential sign. You are using a simple lambda, but you can use k, you can use mu, as long as you're able to define. So I want to define this mu. I mean this lambda here is either e raised negative lambda, lambda raised to x over x factorial. So number one, we are saying that this is a discrete distribution. Just like binomial is discrete. That means you're dealing with the number of customers, number of vehicles that are entered at the service point. Then we are also saying that it is used as an approximation of binomial. So used as an approximation of a binomial distribution. So that's a binomial distribution. What? You see, we say if the number has no mean and standard deviation, then you can approximate by binomial. But they're also saying now we can approximate binomial by Poisson. And when do we approximate binomial by Poisson? When, so use an approximation of a binomial distribution when number A, n is not defined. That means it's not given or not known. When the value of n, when the sample size is not defined, like how many customers are likely to serve today, you are asking somebody in the morning. You will not be able to define exactly how many he or she is able to serve. How many vehicles are likely to pass on this road? You will not be able to tell. You cannot be able to tell at the end of the day, but not in the morning. So when n, the value of n is not known, then you approximate binomial by Poisson. Similarly, n may be given, but n is very large. So when n tends to infinity, or the book just say when n is greater or equals to 10. We are saying when n is large. You cannot expand a value when n is large. For example, in a binomial expansion, somebody said, what is a plus b raised to 0? Suppose the number raised to 0 is 1. Then a plus b raised to 1 is a plus b. Then a plus b raised to 2 is a squared 2ab plus b squared. Then a plus b raised to 3 is a cubed 3a squared b, 3ab squared, b raised to 3. You see, look at the space at the time I'm taking to expand. What if someone said, what is a plus b raised to 75? Or what is a plus b raised to 1042? So when n is large, when n tends to infinity, it is not possible to use a binomial distribution. We approximate by using Poisson. And finally, when the probability of success, when p tends closer to 0, some books will say when p is less or equals to 0.1, when the probability of success is very small. We only use Poisson when the outcome is so rare. Like, for example, when you look at a disease in a population, and the occurrence of the disease is so rare, that maybe in 1,000, one individual is infected. When you look at production, maybe in 1,000, only 1 or 2 items are faulty. That means the occurrence of the event is very rare. when we use Poisson distribution. So when the probability of success is closer to 0 or less equal to 0.1, so books are saying when the probability of success is rare, that is when you can use Poisson to approximate for binomial. The property number 3, we are saying that the mean is the same as the variance, which is the same as lambda. So this lambda symbol that I'm basing on, that's actually the mean. That is the expected value. That is the average. And the mean of a Poisson distribution is the same as the variance of a Poisson distribution. So that therefore follows that a Poisson distribution has only one parameter. Only one parameter. That is a lambda. A parameter is a descriptive index. It's used to describe the characteristics of a population. So this Poisson has only one parameter. Then because we are using it to approximate binomial, we also say it is positively skewed. Because of the approximation to binomial. And we are also saying it has a finite number of times. Finite number of times. Of course, it is. So those are the properties of the 3 commonly used distributions that we have. One continuous, that's normal, then 2 discrete, that's binomial and Poisson. So we need to focus on the examples of each. Look at the binomial one, look at the Poisson one, be able to look at a normal distribution also one. So start with a simple illustration of a binomial distribution. So let's look at example 1. Example 1. And I'm saying this example 1 is binomial. I'll be able to tell you why it's binomial. That we are saying that 2% of the items delivered in our departmental store are faulty. That every time you receive items in the store, 2% of those items are found to be faulty. But find the probability that in a sample, of 8 items, none is faulty. Then I also say 2 are faulty. Maybe at most 2 are faulty. Then I also say maybe at least 6 are faulty. Then somebody may say, find the expected value, find the mean or expected value of the experiment from the supplies. Then of course, if you find the expected value, you're going to proceed and find the variance, the standard deviation of that. So they are saying 2% of the items delivered to our departmental store are faulty. But every time you receive items, 2% are found to be faulty. So this is known. Now somebody's asking us, find the probability that in a sample of 8, you see n is given. These are items. That becomes discrete. N is given. But what is the value of n? The value of n is less than 30. The value of n is less than 20. So because the value of n is given very small, then it goes ahead to become binomial distribution. If this n was given, but n is tending to infinity, n is so large, then you cannot use binomial. But because n is given, but n is small, it becomes a binomial distribution. Why not normal? Items are not continuous. Items are countable. So this becomes a binomial distribution. So find the probability that out of 8 items, and you have selected a random from the store, none of those items is faulty. 2 are faulty. At most 2 are faulty. At least 6 are faulty. Or find the mean or the expected value of this experiment, of the number of items that are faulty in the departmental store. So what we are saying, that a binomial experiment is given as f of x is probability of x equal to x, or just b into np is n over x, p raised to x, q raised to n minus x. It is you who is supposed to define the value of p and q. Now, n is the number of items you select in the sample. So n is the sample size. And we have said that n is equal to 8. Out of the 8 items, now we have said, if p, let p be the probability of getting a faulty item. And the item is faulty. But of course, you can also say, let p be the probability of getting a good item. We will interchange. So that means 2% were faulty. It therefore follows that p is 0.02. 2% is the same as 2 over 100. So we're getting 0.02. So the probability of getting a faulty item is 0.02. Now, Q is the probability of getting a good item. Of getting a good item. And we have said that an item is either good or faulty. So therefore, P plus Q is equal to 1. Now that you know P, automatically you know Q. So then this follows that Q is equal to 1 minus P, which is 1 minus 0.02, which is equal to 0.98. So the probability of getting a good item in our store will be 0.98. So if you know P and Q, then you can now proceed and find the probability. So we are saying, first, we have talked of in the formula of H nx. This one means n over x. Book will say this n combinations x. What they are telling us here is that in how many ways can you be able to identify x items out of n without following any defined order? So combinations is a counting technique where we do not follow any order. You pick items the way they are given haphazardly without following any order. No systematic order is followed. So in how many ways can you be able to pick x items out of n without following any defined order? So this n over x or n over is n combinations x. The number of times, the number of ways you can pick x items out of n without following any order, which is defined as n combinations x is n factorial over x factorial is n minus x factorial. I hope you remember the factorial and permutation combinations. Now, a factorial is the product of all elements below a given number up to 1, where the number is inclusive. So if we talk of n factorial, this is n factorial. This one means n factorial is equal to n times n minus 1 times n minus 2 up to 1. It is the product of all elements below n up to 1, where n is inclusive. So if you are given 7 factorial, for example, it will be 7 times 6 times 5 times 4 times 3 times 2 times 1, which gives you 54. This answer, this simple is on your machines. So once you press 7 and the factorial simple, you just get 54. So if we talk of 8 factorial divided by 6 factorial, there's no need of saying 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 divided by 6 times 5 times 4 times 3 times 2 times 1. Then you start calculating 6, 5, 4, 3, 2, 1. 6, 5, 4, 3, 2, 1. Going to 8 and 7 giving you 56. There's no need of wasting time doing like this. But the factorial simple is on your machine. That's the calculator. So you press 8, then the factorial simple. On the machines, it is given as x factorial. So you press 8, with that simple x factorial, it will give you 8 factorial. The division sign, then you press 6, the dash symbol has x factorial, gives you 6 factorial in equal sign, gives the answer 56. So it's the product of all elements below a given number where the number is inclusive. But you need to note that 1 factorial is equal to 0 factorial is equals to 1. 1 factorial is equal to 0 factorial is equals to 1. So I want us to proceed then and find the answers, the experiment, the outcome of the items delivered to the departmental store. But once you know factorial, then you can now be able to work out combinations. And you can be able to work out permutations. I'll be able to define that later. So number A said none of the items is faulty. So number A, probability of X is equals to 0. None of the items is faulty. So we are saying this is nx, p raised to x, q raised to n minus x. So x here over the number of faulty items. So x in this case is the number of faulty items. So in this example, there we say probability of x is equal to 0. It will be 80. That is 0.02 raised to 0 multiplied by 0.98 raised to 8 minus 0.